Hello everyone, today I'll be taking you through the final bit of the project I've been working on, stock market prediction using AI for better investments. Basically, the contents will be the introduction bit, the background, the literature review, basically what we have learned and what we have done in that section for predicting stock market prices. Then the methodology we have used, our results and discussions. Then I'll also include a link to my dataset and Python notebook. For the introductory bit, I'll begin off by saying, basically what we're doing was an AI project whereby artificial intelligence systems are systems which are able to comprehend something from somewhere they have learned, that is maybe in machine learning, and basically intelligent systems are able to perform complex tasks. So that is what they do. But for this bit of the project, as I said in my earlier videos, we shall be using linear regression model, which is a category of supervised learning and falls under machine learning. So we're going to be using this model to be able to predict stock prices such that investors will know when to buy what shares from that stock, such that they'll be able to obtain better profits. Now, looking at the background, stock market prediction is the act of trying to determine future value of company stock or financial instruments traded on an exchange. We went through the stock market before. I told you what happens, and we know that in the stock market, there are non-linear patterns to it, and a lot of data is collected around it. So for someone to analyze this data, it's quite hectic. So the traditional methods they use to analyze it manually, but they're not able to obtain the right time to invest. So what our model is doing, it's allowing us predict that change in price such that we shall know when to invest. For our integrity of this system, we're looking to ensure there's consistency and it's actually functioning as the way it's supposed to be done. It's functioning like it's supposed to do exactly what it's doing. So we did code reviews and testing to ensure integrity of our system, among others. Then looking at some of the other good techniques that we might have used, we'll look at the long short-term memory. This one, I didn't much choose that model because I chose linear regression for its simplicity, it's fast, efficient, also it's good for continuous data. That is why for this project, I picked on linear regression. And some of the gaps that linear regression model faces, there's outliers. The linear regression model is very sensitive to outliers. So in cases of many outliers, you can have errors in accuracy. Yeah, you can have a model which is not very good. Then we have overfitting. Then we have linear regression. Then assumptions. Linear regression and assumptions. Assumptions here, the model assumes that there's a linear pattern between the independent and the dependent. The linear regression and assumptions there, the model is taking the independent and the dependent to have a linear pattern between them. So those are some of the circumstances and the downfalls to linear regression. But other than that, it's simple to use. That's why I chose it, and it's easy, fast, efficient. For the methodology, we basically obtained our data set from the Tesla data set, which was ranging from the year 2010 to 2022. And it's a time series data, which consists of date recorded, the open cells, the high, the low, the adjunct clause, and volume. So time series data is continuous data, which is recorded over time periods. So that's the data we shall be using to train our model. First of all, we clean the data set, ensuring there's no missing values or records. Then after that, we do exploration and obtain patterns of interest and any pattern available in the data set. So we looked at many ways. We did box plots, we did outlier plots, we did a heat map, correlation matrix, and also a scatter plot, which falls under future independence plots. So this was a sample of part of our data and the description of it. So after cleaning, we checked and we didn't find any form of missing values or records. So we were good to use our data. So this is the correlation matrix that we obtained, which shows a relationship between attributes. As you can see, first we have open, open, that's relation between open and open. One, it's very high. And that's how the correlation matrix looks like. For the heat map, we plotted the correlation heat map, which uses the correlation matrix to plot. Then we also we did a box plot whereby the circles which are above the straight line, those are known as outliers. Then those straight lines are called whiskers. They are the end of the plot. Now outliers are those values which range outside. It's not good to have very many outliers. So in our data set, we had to eliminate them through splitting our data and categorizing into very high values and low values, which we did here in the splitting illustration. Splitting to deal with outliers, that was the first bit. We split our data into two parts, one for very high values and one for very low values. Then, as you can see, this was a scatter plot. Then later on, we went ahead, we split the data which we categorized into high and low values. We each split them into train, evaluation, and test data sets. In order for us to test, train our model and later evaluate. So on training our model, we're able to train it, then we're able to also evaluate, then do testing. For evaluation matrix, since this was linear regression model, we used the mean square error and the R-squared score. So this basically shows you how we did it and the formulas we used, whereby the mean squared error is helping us get the error, because in the line of regression, which we use in linear regression, which is that red line, To find the mean squared error, it's finding the distance from that red line to the actual value. So you're getting the error between the predicted and the actual value. That is how we get the mean squared error. So that is what we used for our evaluation metrics. And once you have a mean squared error, which is because it starts from 0, there are no negative values, it starts from 0, the more it tends towards 0, the better it is. As for the R-squared score, it's about the same thing, but it's better to have values which range between 0 and 1. The R-squared square values range from 0 and 1. The values tending towards 1 are better values. It means that your model fits and it's neither underfitting or overfitting. Then tuning hyperparameters. This is how we try to make our model fit and work with linear regression. So this is after us categorizing it into two and splitting it into high and low values. This is how, whereby here we had very few outliers, and here in the high values, we didn't have any outlier. So our model was actually quite good. So basically that is it. Thank you for listening.